Hello and welcome to my channel. In this series, I will be making some videos on algebra concepts. And the first video we want to talk about here is the set theory and real numbers. The set theory and real numbers. So when you say a set refers to the collection of objects, the collection of objects. Now the set can be written in two notations. The first one is known as the roster notation, the roster notation. And the second one is known as the set builder notation. Okay. Right, so two ways of naming a set. So let's consider each of them. Consider a set that's made up of the numbers 2, 4, 6, and 8, right? Now, in the roster notation, we use the curly brackets, right? So you write the numbers within the bracket, as you can see over here. Okay, that is the roster notation. Okay, so roster, like you are listing items or certain objects in the curly brackets. Then when we talk about the set builder notation, this is where you write it in this format. So you have a curly brackets, and then you define the variable x. So you're going to say x. And then with this vertical line, which we read as such that, then you can define the set of numbers that you have here in words, like using just a basic sentence to define what you see. Now, if you look at 2, 4, 6, 8, you can say that this is the set of numbers or set of even numbers between 1 and 9, right? Okay, we can define it in that format. So we can say x is an even number between 1 and 9. Okay. And I close the brackets. Okay. So if you write it this format, then you've written it in the set builder notation form. Set builder notation. All right. So that's what you have here. Okay. So this is how you're going to read the set builder notation. You say x such that, or given that x is an even number between 1 and 9, right? So that's how you read what we have here. Okay. Now let's now define two sets, set A and set B. Set A and B. So set A is made up of 2, 4, 6, 8, and set B is made up of 2, 6. Now the number 4 is a member of the set A. So 4 belongs to A. You can see 4 over there. We can say that 2 is also a member of set A. 6 is a member of set A. 8 is a member of set A, and so on. 6 over here is a member of set B, and 2 here is also a member of set B, right? So each element that you see within the set is called a member, right? And in math, we can write this using a notation. So we can write 4 is a member of the set of set A as 4, and then this symbol represent an element or belongs to, right? The set A, right? So see the symbol, it stands for belongs to, or it's a member of. Okay, so each member of the set is referred to as an element. So let's write another example here. So I can write 6, or say that 6 is an element of A. Or we can also say 6 is an element of the set B. There is another symbol which refers to does not belong to or not an element of. So if I have this symbol here and then put a slash or a line through it like this represents not an element or not a member. Or does not belong to the set that you're talking about, right? So an example would be, if I look at set A and B again, I can say that the number 7 does not belong to, or it's not an element of the set A. Right. So that's how we represent it's not an element of something. Now let's talk about something known as a subset. Subset. So set B is a subset of A. Why? Because all the elements of set B can be found in the set A. So we say that it's a subset of A, right? So let's go back. So look at set B, you have 2, 6. Now I can find 2, 6 within set A. Because of that, the set B is a subset of the set A. And then there's a symbol for that as well. And the symbol is what you see here. This represents the symbol for subset, okay? So you see B is a subset of A, if you are reading this here. B is a subset of A. Now, we can also have a situation where the element or the set is not a subset of any given set. So let's say that if I take another set C and define this as 7, 8, we can say that the set C is not a subset. So not a subset, we put a line through it like this. It's not a subset of A. All right, so this represents not a subset. not a subset. We have to distinguish between what we call the subset and then a proper subset. Proper subset, right? So let's do that. Now, the number of elements in set B is not equal to the number of elements in set A, all right? So it is a proper subset of A. So let's go back to the example. So we've already seen that B is a subset of A because you can identify all the elements in B or in A, right? Now, if you count the number of elements that I have in B, you have 1, 2. You have 2 elements, 2 and 6, so 2 elements. Whilst you have 4 elements in A, right? So because the number of elements in B is not the same as that in A. In other words, you have fewer elements in B than A. B is a proper subset of A, right? In other words, you have less elements here than in the other sets, okay? And the symbol for that is this. So if you see the symbol, it represents a proper subset. Okay. So we can rewrite what we have initially as B is a proper subset of A. Let's look at another example. Let's call this set C, made up of 4 and 8. Now 4 and 8, I can identify the same elements in set A. You have 4 and 8 here, right? Which means that C is a subset of A, all right? It's a subset of A. Now, because I have 2 elements here, 1, 2, the number of elements here is less than the number of elements in set A. So I can say that 4 is a proper subset of, I can say that, sorry, C is a proper subset of A, a proper subset. Okay. Now let's come up with another example. If I tell the set D is made up of 2, 4, 6, 8, is D a subset or proper subset of A? Let's see. You have 2, 4, 6. All the numbers here, I can find them in A. So D is a subset of A. That would be true. But it's not going to be a proper subset because the number of items that I have here, I have 4 items here, 4 elements here, and the same 4 elements here. So this is not a proper subset. So we can write this as D is a subset of A. So sometimes the way I look at this in terms of less than or greater than or equal to symbols, if you think about it, it also helps. So think about this proper subset as like as a less than symbol, right? So we say that number of elements in C is like less than the number of elements in A. Okay, that's what this means. Okay. Now this one will represent something like less than or equal to, right? So the number of elements in D is equal to that of A, right? So if you think about that way, that also helps you to remember. So proper subset has to be less than. The element has to be less than. When it's regular subset, then it could be more, it could be less or equal to, right? Less or equal to. If you think about it that way, it helps you to also remember. Now, we also want to talk about intersection. Intersection represents the number of elements that they have in common. Okay? In other words, where do they overlap? Okay? And the intersection symbol is this, the inverted U, intersection symbol. So it refers to the elements common to all the sets under consideration. So if I take set A and B again, what do they have in common? You have 2 in common and they have 6 in common, right? So the intersection, so B intersection A is going to be the set 2 and 6, the elements that they have in common, 2 and 6. Okay. So with this knowledge, we now want to look at real numbers. What are real numbers? Now, real numbers refers to the set of all numbers used in everyday life activities, right? Real numbers. There are different types of real numbers. We have numbers that are called the natural numbers or the counting numbers. And these are the numbers for counting, right? So it's defined by the set 1, 2, 3, 4, and so on, right? These are the numbers used to count. So they are known as natural numbers. Then you have the whole numbers. Whole numbers is made up of a set of natural or counting numbers with 0 included. So all the natural numbers 0 included. So we can define this as a set 0, 1, 2, 3, 4, and so on. These are the whole numbers. Okay, so it's the natural numbers together with the whole numbers. Then we move on to the integers. So integers. So the set of all whole numbers and their opposites. Opposites represents the integers, whole numbers and their opposites. So we can look at example like -4, -3, -2, -1, 0, 1, 2, 3, and so on, right? So numbers all the way to the whole numbers negatives, and then whole numbers that are positives, including 0. So that would be integers, called the integers. Okay. Then we have rational numbers. Rational numbers. So these are numbers that can be expressed as an integer divided by a non-zero integer, right? So mathematically, we write this as the set made up of P divided by Q, such that P and Q are integers, but Q cannot be equal to 0. In other words, the denominator cannot be 0, but it can be any integer. That means whole numbers, okay, and their opposites, including 0. Okay. But remember, the denominator cannot be 0. Okay. So we can write, it means that rational numbers can be written using fractional or decimal notations. For example, if you have 5/8, 5/8, 5 is an integer, 8 is an integer. So you have P/Q, integer divided by integer. So that makes this a rational number. 12 is an integer, -7 integer. So you're dividing an integer by an integer. So we have a rational number. The same for these two examples, 37/1 and a 0/6. 0/6, 0 is an integer, 6 is an integer. So this is a rational number, right? Think about it, 0/6 is equal to 0. So 0 is part of the integers, right? So that makes this a rational number, okay? But we cannot have something like 6/0. This is undefined. It's no value for this. So that's why we are saying that the denominator cannot be equal to 0. Okay, that's not good. All right. Now, if you have a rational number and you change the rational number to the decimal form, right, what we call the decimal notation. Now, the rational number will either terminate or repeat. You have a terminating decimal, or you have a repeating decimal, okay? Terminating or repeating decimal. Once you get that, then you're looking at a rational number. For example, 5/8. If I change to decimal, I'll get 0.625. Now this has an end. It ends here, right? 0.625. Because it has an end, it terminates. So this is an example of a terminating decimal. It terminates. Okay. What about 6/11? If you take 6/11, if you change the decimal, you get 0.5454, keeps going. So the dots at the end means it keeps going. We can shorten this to this form. You just write 0.54, right? So because 54 repeats, you just write it once and then put a line over the group that repeats. Okay, so you have 0.54 and then put a bar over it. Okay, so this is what this means. It means you have the block of numbers 54 keeps repeating 54, 54, and so on. Okay, so this is an example of a repeating decimal, a decimal that repeats. Repeating decimal. Okay. Let's take 1/3. Now, if you take 1/3, if you change the decimal, you get 0.3333. That's the end. So dots at the end. That's the end. So instead of writing this way, you can write it as 0.3 and then put a bar over the 3. It's 0.3 with a bar because the 3 repeats. Okay, it repeats. So write it once and put a bar over it, 0.3. So this is another example of a repeating decimal that repeats. Okay. So because of that, these are all rational numbers, right? So you can use the two definitions to check if a number is rational or not. The integer over an integer, it will change to decimal form. It either repeats or terminates. Repeats or terminates. Okay. Now let's take some other examples. What are square root of 4? Let's go square root of 4. Now square root of 4, it gives us 2, right? 2 times 2 is 4. So square root of 4 is 2. Now what are 16? 16, square root of 16 is also 4. That's 4. It's 4. Now, are these rational numbers? Yes, they are rational numbers because 2 is the same as 2/1, integer over integer. So that's rational. What are the 4? 4 is 4/1. So that makes it an integer. Okay, we have 4/1 as integers. So what we have here is a rational number. So these are rational numbers. Okay. Now, what are non-integers? Non-integers. Now, non-integers refer to numbers that are rational, but they are not integers. Okay, they are not integers. Number, they are not whole numbers and they are opposites, including 0. Okay, so this includes fractions, and terminating or repeating decimals, then those will be non-integers. Non-integers. Okay. So examples, if I have 1/2, that is a non-integer. 0.51. This is a non-integer. Okay, and so on. Negative 2.5, non-integer. Okay. And then the last classification of real numbers will be the irrational numbers. Irrational numbers. So these are numbers which do not fit into the definition for rational numbers. In decimal notation, they are non-terminating and non-repeating decimals. Non-terminating, non-repeating decimal. They don't repeat and they don't terminate. Okay. Example, if you take 0.6748 with dots at the end, it means that it keeps going. You don't see any pattern of repetition within this. Because of that, this number is an irrational number. Now, square root of 2, if you use your calculator, just square root of 2, you realize that it's a long number, has no end, and doesn't repeat. Okay, so that would be an example of irrational number. Pi is a very long number. 3.14 keeps going, very long number, has no end. Because of that, this is an example of a non-terminating, non-repeating decimal. So pi is an example of irrational number. Square root of 3/2. Square root of 3. If you check the square root of 3, it's a long number, decimal with no end, and doesn't repeat. So since this is non-terminating, non-repeating, if you divide by 2, it's going to give you a non-terminating, non-repeating decimal. So square root of 2 of 3/2 is going to be an irrational number. So that's how you can classify the different numbers that we have. So to summarize, we can create a flow chart. So we can start with real numbers. You have real numbers. Then we can break this down into numbers that are rational and numbers that are irrational. Okay. Now the rational numbers, we can have the whole numbers, and then we have the non-integers. Okay, so the whole numbers, we can break this down into 0 and the positive integers. Okay. So let's include the negative integers here. Then the positive integers, we can call them the counting numbers or the natural numbers. Okay, so this is a summary of the different numbers that you have. Okay. So I hope you've learned something from this video. I'll see you next time with a lesson on algebraic expressions.